In this episode, we look at several attack surfaces that often sit in plain sight: ports, services, applications, race conditions, and malicious updates. These topics may sound separate at first, but they all connect to the same practical question. Where can an attacker interact with a system, and what can go wrong when that interaction is unnecessary, poorly controlled, or timed in a dangerous way? A port is a communication doorway into a system. A service is the program or function listening behind that doorway. An application is software that performs useful work, but may also contain weaknesses. A race condition happens when timing affects security or correctness. A malicious update abuses trust in the update process itself. When you understand these ideas together, you can see why defenders care so much about reducing exposure, hardening systems, testing applications, and making sure trusted updates really come from trusted sources. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. A port is a logical communication point that helps systems send and receive network traffic. You can think of a device as having one network address, but many possible communication doors at that address. Different services listen on different ports, so traffic reaches the right function. A web service, remote access service, database service, or file sharing service may each use different ports. Ports are not dangerous by themselves. They are part of how networks work. The risk appears when a port is open and reachable even though the service behind it is unnecessary, vulnerable, misconfigured, or poorly protected. Attackers often scan networks to find open ports because open ports tell them where conversation is possible. An open port is not proof of compromise, but it is a clue. It says a system is willing to receive a certain kind of traffic, and attackers want to know what is listening. Services are the active functions that respond on ports. A service might host a website, allow remote administration, provide name resolution, share files, support printing, expose an application programming interface, API, or connect to a database. Many services are legitimate and necessary, but each running service increases the attack surface. Attack surface means the set of places where an attacker can interact with a system or environment. A service that is not needed should usually not be running, because it creates exposure without business value. A service that is needed should be patched, configured securely, monitored, and limited to the people or systems that should use it. This is a major part of hardening. Hardening means reducing unnecessary weakness by removing what is not needed, securing what remains, and making unsafe defaults safer. You are not trying to make systems unusable. You are trying to make every open path defensible. Unnecessary exposure is one of the easiest gifts an organization can give an attacker. A service may have been opened for testing and never closed. A database may be reachable from more networks than intended. A remote administration port may be exposed to the internet because someone needed quick access during an emergency. A file sharing service may remain enabled even though no one uses it anymore. Attackers do not need to know the history of why the exposure exists. They only need to find it. Once they do, they may try default credentials, stolen credentials, known vulnerabilities, weak configurations, or brute force attempts. Brute force means repeated guessing, often against passwords or keys. The safer approach is to ask whether the service must be reachable, who truly needs it, and whether a safer access path exists. Exposure should be intentional, limited, and documented, not accidental. Applications create another major area of vulnerability because they process input, enforce rules, connect to data, and make decisions for users. A vulnerable application may allow an attacker to bypass access controls, read data they should not see, change information, disrupt service, or run commands in places they should not control. Some application weaknesses come from coding mistakes. Others come from insecure design, outdated libraries, weak session management, poor input validation, or unsafe permissions. Input validation means checking data before trusting or processing it. If an application accepts whatever a user sends without careful checks, the attacker may shape that input to confuse the application or make it behave in unintended ways. Applications are valuable targets because they often sit close to business processes and sensitive data. A public-facing application is especially important because attackers can reach it directly without first entering the internal network. Vulnerable applications are not always obviously broken. A website can look polished and still have weak access control. A business portal can function normally while allowing users to reach records that do not belong to them. A mobile application can feel smooth while exposing sensitive information through the way it communicates with backend services. A custom internal application can be risky because it was built quickly and never reviewed deeply. Attackers test applications by looking for assumptions. Does the application trust the user too much? Does it reveal helpful error messages? Does it allow someone to change a value and see another person's data? Does it rely only on the user interface to hide restricted functions? Does it use outdated components with known weaknesses? The security concern is not whether the application works for honest users. The concern is whether it behaves safely when someone intentionally pushes it in the wrong direction. Ports, services, and applications connect because a port often exposes a service, and the service often supports an application or function. Imagine a customer portal reachable from the internet. The open network port allows web traffic to arrive. The web service receives that traffic. The application processes requests, checks identities, retrieves data, and returns results. A weakness at any layer can create risk. The port may be exposed too broadly. The service may be outdated. The application may mishandle authentication or input. The database behind the application may allow too much access. Attackers often move through these layers patiently. They begin by finding what is reachable, then identify what software is present, then test how it behaves. Defenders respond by reducing unnecessary exposure, keeping services updated, reviewing application security, limiting backend access, and monitoring for unusual behavior. Security improves when each layer supports the others. Race conditions are a different kind of weakness because they involve timing. A race condition happens when the result of a process depends on the order or timing of events, and that timing can create an unsafe outcome. In everyday terms, imagine two people trying to update the same record at nearly the same moment, and the system handles the order incorrectly. In security, the concern is that an attacker may take advantage of a small timing gap between a check and an action. The system may verify that something is allowed, but by the time it performs the action, the condition has changed. If the system does not handle that change safely, the attacker may gain access, change a file, bypass a restriction, or cause inconsistent results. Race conditions can be hard to find because the system may behave correctly most of the time and fail only under specific timing. Time of check to time of use, TOCTOU, is a common way to describe one type of timing weakness. The system checks a condition first, then uses the result later. The danger appears if the condition changes between the check and the use. For example, a system might check whether a file is safe to access, then open the file a moment later. If an attacker can swap or alter the file in that gap, the system may act on something different from what it checked. You do not need to focus on file details to understand the pattern. The system made a decision based on one reality, but acted after the reality changed. TOCTOU problems can appear in access decisions, file handling, transaction processing, temporary resources, and shared systems. Secure design tries to make the check and action happen in a way that cannot be manipulated between steps. Race conditions matter because attackers sometimes look for tiny windows of opportunity. They may send many requests quickly, try to trigger two actions at once, or create unusual timing that normal users would never produce. A shopping site might process a discount incorrectly if two requests arrive at the same time. An account system might allow a restricted change if approval and modification steps are not tied together safely. A resource reservation system might double assign something if updates are not handled carefully. In some cases, the impact is minor. In other cases, timing can affect money, access, data integrity, or system stability. Integrity means information remains accurate and trustworthy. Defenders reduce race condition risk through careful application design, proper locking, transaction controls, safe file handling, and testing under unusual timing conditions. The deeper lesson is that security is not only about what a system checks. It is also about when the system checks it. Malicious updates are another serious threat because they abuse one of the most trusted parts of technology maintenance. Updates are supposed to fix bugs, add features, and close security weaknesses. Users and administrators are often trained to trust updates from vendors, app stores, device management platforms, and internal deployment systems. Attackers know that trust is powerful. If they can compromise an update process, sign a harmful update, take over a vendor account, poison a software package, or insert malicious code into a trusted distribution path, victims may install the attacker's code voluntarily. This is especially dangerous because updates often run with elevated privileges. Elevated privileges mean higher levels of system permission. A malicious update may be allowed to change files, install services, or reach sensitive parts of the system because legitimate updates need those abilities. Trust in updates must be protected carefully. Malicious update risk can appear in several ways. A vendor's build environment may be compromised so malicious code is inserted before release. A package repository may host a harmful version of a component that developers unknowingly include. An attacker may create a lookalike package name to trick someone into choosing the wrong dependency. A software distribution account may be taken over and used to publish a harmful update. An internal deployment system may be compromised and used to push malware across many machines. The common theme is trust inheritance. If a trusted channel delivers something harmful, the victim may accept it because the channel looks legitimate. This is why software supply chain security matters so much. Defenders must care not only about the final application, but also about where updates come from, who can publish them, how they are verified, and whether the process can be monitored. The relationship between malicious updates and ordinary patching can feel uncomfortable because security teams strongly encourage updates. That advice is still correct. Most of the time, timely updates reduce risk by fixing known weaknesses. The answer is not to avoid updates out of fear. The answer is to make the update process trustworthy. Organizations may verify digital signatures, use approved repositories, control who can push updates, test updates before broad deployment, monitor deployment tools, and keep emergency rollback plans. A digital signature helps confirm that software came from a trusted source and has not been altered in an unauthorized way. Testing helps catch problems before they affect everyone. Monitoring helps detect unusual deployment behavior. Rollback planning helps recover if an update causes harm. Good update security balances trust and verification. You want patches to move fast enough to reduce exposure, but through channels that are controlled and observable. Attackers look for unnecessary exposure and timing weaknesses because both can turn normal system behavior into opportunity. An open port may give them a place to start. An unnecessary service may give them something weak to attack. A vulnerable application may give them a way to reach data or identity. A race condition may give them a timing gap that bypasses intended controls. A malicious update path may give them a trusted way to distribute harmful code. These are not random issues. They are all examples of systems doing useful things in ways that become risky when trust, access, or timing is not controlled. Defenders reduce the risk by making exposure intentional, minimizing what runs, securing applications, designing safer processes, protecting update pipelines, and watching for behavior that does not fit normal use. Security is often about narrowing the attacker's options before an incident starts. As you continue with Security Plus version 8 and SY0801, remember that ports, services, applications, race conditions, and malicious updates all show how ordinary technology can become an attack surface. Ports allow communication, but open ports reveal reachable paths. Services provide useful functions, but unnecessary services create avoidable exposure. Applications support business work, but vulnerable applications can mishandle input, access, and data. Race conditions expose the danger of unsafe timing, especially when a system checks one thing and acts later under changed conditions. Malicious updates abuse trust in the software maintenance process. The practical security habit is to ask what is exposed, what is running, what is trusted, what can be reached, and what could change between decision and action. When you think that way, you begin to see risk not as a mystery, but as a set of paths that can be reduced, monitored, and controlled.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.